Welcome PCS members and friends to our today's Tuesday PCS IBS seminar. It is a great pleasure to have with us today Professor Donna Sheng from California State University. And I would like to invite our scientific host, Alexei, to introduce our speaker. Please, Alexei.
Yes, Dylan, thank you. Yes, as Dylan announced, our today's speaker is Professor Donna Sheng from California State University, Northridge. So let me briefly introduce the speaker. So Donna received her PhD from Nanjing University in 1989 and then moved to Texas Center for High Temperature Superconductivity for 10 years. And since 2000, she's a faculty at the California State University. And she also has affiliation with the Princeton Center for Complex Materials. So she works in the area of many-body condensed matter systems, and with particular interest in exotic states of two-dimensional materials like frustrated magnetic systems and quantum Hall physics. And she's also interested in working on developing new numerical methods, including exact diagonalization, de-emergy, and variational quantum Monte Carlo. And so with this, let's welcome our speaker. And please, Donna, the screen is all yours.
Thank you. I want to thank the organizer for giving me this opportunity. So today I'm going to talk about the, Today I'm going to talk about robust D-wave superconductivity of doped Mott insulator and square lattice. So I'm Donna Sheng. This work has been done in collaboration with So Gong from Beihang University and Wei Zhu from Westlake University. My research in this direction is supported by Department of Energy. So here is the outline of my talk. I'll first have a brief introduction to high TC cuprates as doped Mott insulator and review numeric study and theoretical study in this field. Then I will present our numerical results based on the density matrix renormalization group method. Our study is based on the extended TGM model. We'll demonstrate a global phase diagram with different quantum phases, including a uniform D-wave superconducting phase. And that phase has robust superconductivity. In our quantum 1D system, that the superconductivity demonstrates very slow decay in real space with a power law exponent, which is much smaller than 1. Then we also identify a superconducting phase coexisting with charge density wave phase. Then I'll give a brief summary. So the high TC cuprate were discovered in 1980s, and there are different cuprate compounds with very high critical temperature. That's the mechanism of high TC superconductivity has attracted a lot of theoretical and experimental studies. We can, before the discovery of cuprate superconductivity, we understood superconductivity basically based on the BCS theory, where we have a Fermi surface and the quasi-particle around the Fermi surface are paired due to the attracting interactions. In that Fermi surface picture, there is the characteristic the Fermi-degenerate temperature. That temperature is determined by Fermi energy, and that temperature for cuprate is around 10,000 K. Then we can examine if the cuprate has the typical Fermi-liquid behavior through measuring the specific heat, polysusceptibility, and 1/T1 NMR spin lattice realization rate. If they are Fermi-liquids, the pairing of the quasi-particles and the Fermi surface, then those quantities will follow definite behavior, like specific heat has a linear T behavior. The polysusceptibility is a constant. However, experimental results indicated all those behaviors are not observed in experiment. For example, the gamma has those almost linear T dependence of the coefficient gamma above the critical superconducting temperature. At the same time, the polyspin susceptibility is also very depends on the temperature, and the 1/T1 behavior is also different from linear T dependence. Those indicated our system are quite different from the pairing of Fermi-liquids. So the starting point first proposed by Phil Anderson is from the strong correlated point of view by doping the Mott Insulators with antiferromagnetic order. And others experimental picture supporting that picture is the observation of antiferromagnetic order at lower doping and the pseudo gap above the superconducting critical temperature, as well as the charge density and spin density waves above the superconducting temperature. So if we starting from the doped Mott insulator, then the simplest model is the one band Hubbard model with a parameter hopping of electrons and also on-site Hubbard interaction. In this picture, on square lattice, if we go to undoped case, then we have antiferromagnetic order. And then for the doping case, theoretical picture based on slave particle approach also give us a possible range of superconductivity. The antiferromagnetic order at half filling can be easily understood based on the Mott insulating physics at large U. So with the increase of Hubbard U, the energy band splits into a lower Hubbard band and upper Hubbard band. In the lower Hubbard band, each site is occupied by one electron, and there is a Heisenberg exchange interaction between those nearest labeled electrons. So they intend to form antiferromagnetic order. At finite doping, a simple picture is the resonating valence bond pairing. So due to the spin singlet pre-existing in the half-filling case, through doping, those the spin singlets will form paired paired electrons, and that can move around when we take away some of the electron from those lattice sites. More complex picture may involve the pairing of composite fermions. There are several good theoretical review articles which describe the RVB theory based on the gauge theory, and there are also extensive variational wave function studies. However, because there are no controlled method to directly solve the strong correlated system, such as the Hubbard model in 2 dimensions, extensive numerical studies play important role to determine what kind of quantum phase can be realized in such system. At half-finning, we have a very good understanding of quantum phase diagram. So in the half-finning, the model reduced to the Heisenberg model. If we only consider nearest label coupling, then there is a near-ordered phase. If we allow the competing second nearest label coupling, then there is a possible region for the gapless spin liquid. The open question is if we dope those systems, what quantum phase can be obtained if square lattice can have robust superconductivity. The earlier DMRG simulation and the full-leg ladder does support the superconductivity from both Hubbard and the TGM model. So one case we need to pay attention is in such system, the numerical results actually depends on the band dimension. Because when we take a small band dimension, the truncation error will make the correlations decay exponentially. Only with the increase of band dimension, the correlation can demonstrates like a power law behavior, indicating quasi non-range order. So the earlier numeric study focused on full-leg ladder, which indicated D-wave superconductivity.
Professor Sheng, we have a question from Alexei.
Yes, please.
Yeah, thank you. I have a very naive question. So you mentioned that if you add the second nearest neighbor hopping, you get there's a range of parameters where you get a spin liquid, and then if you dope it, you might expect superconductivity. Is that correct?
Yes. However, even you just dope a magnetic order phase, you may also get the superconductivity.
Okay, that's what I wanted. So my question was basically, if you take a spin liquid state, quantum spin liquid state, and dope it, do you always expect superconductivity, or there might be other scenarios?
And yeah, I think so far numerical suggests that you always get superconductivity.
So, for example, naive questions: if one takes the Kitaev model and dopes it, so you also find superconductivity there, because I believe there things should be a lot more under control.
Yeah. So when I say you always get, there are very limited numeric results on those questions. So I was referred to things like triangle lattice or square lattice, TGM model or Hubbard model. For Kitaev model, there is a paper based on DMRG simulation, which suggests superconductivity, pairing decay much faster than a strong superconductivity. However, maybe superconductivity is in the pre-existing form. Maybe with increasing system use to the real 2D system, it may go into a superconducting phase.
Okay, okay,
Yeah,
thank you.
because of the system V's does play a role. However, there is several important paper based on Simon's many-body electron collaboration. They show that there is the absence of superconductivity for Hubbard model and the six-leg ladder with just nearest label hopping. So numerical simulation are done with, for example, by DMRG with band dimension increase from 10,000 state to 22,000 state, and those are SU2 states, which equivalent to like 66,000 U1 states. So they push to the limit for numerical simulation and find the superconducting pairing correlation basically this decays with distance exponentially. Then they also compare this picture with variational wave function and the quantum color simulation. So if they start from variational wave function where the pairing is being included in the variational wave function with increasing of the quantum color sweep, or with increasing the convergence of quantum color simulation, they found the pairing correlation drops by more than one order of magnitude, and it becomes.
Excuse me, Donna, can I ask you a question before?
Yes. Yes.
So
yes.
I think you mentioned already experimental observation of the D-wave symmetry of the superconducting order parameter. Yes. Can you maybe explain again in simple terms what do I have to put into models like Hubbard or other models in terms of interactions, lattice structure, and so on, in order to expect to, if at all, to get the correct symmetry? What do I have to do?
Yeah. So for square lattice, as long as you consider a large U model or TGM model, if the superconductivity is obtained for some parameter region, the symmetry is indeed the D wave. So that's maybe intrinsically related to the very strong repulsion in such system.
So you want to say that the strong Hubbard interaction is, so to say, guaranteeing you almost D-wave, the D-wave symmetry.
Yeah, for some for the most of recent simulation, the D-wave.
Why is that? Is there a simple way to see that?
Simple way is in the mean field, slave mean field. Yes, it does give the D-wave symmetry, because the D-wave symmetry has additional parameter, like in the X and Y direction, you can have different sign of pairing that allow you to get better variational energy.
Okay, thank you.
Thank you. So for the simplest Hubbard model with only nearest label hopping and wider system like six leg, the superconductivity is absent from those simulations. Very interestingly, if we consider large U Hubbard model, which is the TGM model, then there are three different simulations around the same time. They all identify the superconductivity. So those models, including second nearest label hopping, and which puts the half-filling phase into the phase of doping spin liquid. And so that is the work by Hongchen Jiang that examined the very large T2 over T1, which corresponding to J2 over J1 around 0.5. So in the spin liquid region. However, in the Steve White's work, they find possible pairing extended to the larger region in the sense that even for smaller T prime, they also have the D wave and the P wave pairing, and also those pairing competing with anti-phasor magnetic order. So that's the second work. Then our work will show that you don't need to doping spin liquid to get into the superconducting phase. So let me first put some brief summary about the current understanding of the superconductivity from such Strand U model, Hubbard model, or TGM model. So no superconducting phase for the TGM model with only nearest label hopping. And there are some common features of Hubbard or TGM model. There are charge density wave and the spin density wave, which can compete with other correlations. Then superconducting correlation in some extended model with finite second nearest label hopping can compete with other orders. So that superconductivity can also be observed in those parameter region. The question we want to address is what is a quantum phase diagram for the TGM model, Hubbard model? And like if we have to dope a spin liquid to have strong superconductivity, or if we dope a weaker anti-phasor magnetic state, we can also observe a superconducting phase. Then we also want to ask if superconductivity can emerge in a uniform spin and charge density state.
Professor Sheng, Alexei has another question or comment.
Please go ahead.
Yeah, could you go back one slide, please?
Okay.
So I mean, this result that the nearest neighbor TJ model doesn't have superconducting phase, is that in any way related to the absence, perhaps to the absence of frustration?
Yes. Yes, it's related to and there is no frustration. However, if we just turn on T prime or turn on the J prime, they both can help to stabilize superconductivity. So what kind of frustration can most effectively enhance superconductivity? It's not well understood.
Okay, thank you.
You're welcome. So we have done very extensive study of TGM model. So in our TGM model, we allow the nearest label and the second nearest label hopping and anti-phasor magnetic coupling. So the second nearest label is the causing this square lattice. In our phase diagram, we vary T2 over T1 and together with J2 over J1. So we allow the J2 over J1 ratio equals square root of T2 over T1. And as we would obtain from the Hubbard model at the large U limit. So that is one parameter. Second parameter is whole doping ratio. Then we get 3 different phases. For the small T2 region, indeed, what we get is CDW dominant. When we increase T2 over T1 to be around slightly larger than 0.1, we go into the D-wave superconducting phase with very uniform charge density. If we go to even larger T2 over T1 and also focus on lower doping region, we get superconducting phase coexisting with CDW. So if we just increase the whole doping ratio, then at lower doping, we can be in this coexistent phase. Then doping will induce a transition to the pure D wave without stripe. Another important point is the parameter J2 over J1 is the square of T2 over T1. So only at this much larger T2 region, we can see spin liquid half filling. So our whole phase diagram actually is based on doping the antiphase magnetic ordered state, not into the doping spin and liquid, and which provide evidence that superconductivity is more common in such a system through doping, as long as we increase the fluctuation with the second nearest label hopping and antiphase and the spin exchange. So let's try to discuss the different quantum phase one by one. The first one is the CDW with very small T2 over T1, like a T2 over T1 smaller than 0.1. We get this charge stripe phase. This is electron density as a function of x coordinates of the sample. So it has this period. If we calculate how many electrons inside each period of the stripe, there are approximately 4 electrons inside each stripe. With increasing T2 over T1, we go into a quantum phase where the electron density in the bulk is very uniform. Only at boundary, you have a small boundary effect. We don't have this usual Faraday oscillation for this fermionic system. If we go to even larger T2 over T1, then we also obtain a stripe phase, but this period of a stripe is reduced from the smaller the T2 over T1 phase. And in this third phase, within each stripe, we have 2 electrons. It turns out it's a common case if we have each stripe with 2 electrons, superconductivity usually also emerges. In this plot, we show the pairing symmetry by comparing the pairing correlation for 2 bonds along y direction and the 1 bond along y and another bond along the x. The pairing, is along nearest label. We can set the pairing either along the y direction or along the x direction. We find if 2 bonds are both along y direction, we also always get a pairing correlation, which is positive. But if one pairing is along the x direction, then the pairing correlation is negative, which is consistent with the D-wave pairing symmetry. And also, we compare the pairing correlation. Sorry, we also compare the pairing correlation with different T2 over T1. You can see that for T2 over T1 equals 0, the pairing correlation decays very fast and decays exponentially with distance. But as long as we have a reasonable large T2 over T1, pairing correlation decays very slowly. Then also for those three phases, it has a different shape for the electron Fermi surface. So we cannot identify where is Fermi energy, but for the larger T2 over T1, the Fermi surface has near a circular pattern. And for very small T2, for T2 over T1 equals zeta, we have this open like Fermi surface, and also it breaks the rotation symmetry. So those different features actually characterize three different quantum phases we shown in the phase diagram. As I already mentioned, the bond dimension we use for DMRG simulation is important. So if we keep increasing the bond dimension, the truncation becomes smaller, and we can extrapolate the accurate energy of the ground state through the extrapolation with truncation ether. We can also do extrapolation with 1 over m, 1 over d. D is bond dimension. So when d go to infinity, we obtain the results of infinite bond dimension. And here is an example of extrapolation of pairing correlation, and the example of extrapolation of results for the density correlation. So those extrapolation are very smooth, which gives certainty of the correlation at the infinite band dimension limit, especially for the pairing correlations. So for the first quantum phase, the CDW phase, as we varying different doping level, like from 1 over 24 to 1 over 6, the CDW pattern varies as the stripe period is changed. However, within each stripe period, we always have 4 electrons. The amplitude of pairing of those charge density oscillation does decay powerfully, because this is a quantity 1D system. The power decay exponent is very small. It's around 0.35 to 0.59, which means a very strong quantity order for the charge density. If we look at the single particle and the spin correlation, they both decay exponentially, even when we scale those results to infinite band dimension. So those characterize the insulating CDW phase. Now we look at the density of the uniform D wave phase. For different doping level, the charge density is always very uniform. More importantly, we want to show the superconducting correlation decays powerfully. So here are examples of superconducting correlation for the uniform pairing phase. That for given bond dimension that do decay exponentially, but with we scale those correlation exponent to infinite band dimension, we find the correlation length increase beyond 10. It's around 50 for the largest band dimension we used. If we scale the band dimension to infinity, then the correlation length diverge. So a better scanning method is we directly scale the pairing correlation at different distance to infinite band dimension. then the resulting pairing correlation curves following the power law decay. The power law decay exponent K superconducting is around 0.3. So it decays much slower than 1 over X. X is 1 over R behavior. So that indicates very strong superconducting correlation. We can also compare our system with different system V's. Like system V is equals 6 has pairing correlation decay much slower than the system with V's 4. So 6-leg ladder behaves more like 2D system with much slower decay pairing correlation, which indicates the superconductivity may remain robust in a 2D limit. And here is another example. The previous results I used the doping level 1 over 12. And now we look at the doping level 1 over 8 with a larger T2 over T1. In this case, we still find power law decay superconducting correlation with the exponent around 0.36. So for different doping level, we always find that intermediate phase has very robust quasi non-range order for superconducting correlations. Now we compare this pairing correlation with other correlations. So we changed the scale of those correlations because the pairing always proportional to delta square. If we renormalize it with delta square, then those correlations has a value around 1 at short distance. We did a similar rescale for green function and the spin correlation. So they are all in the same order at short distance. Then we can see very clearly at non-distance, the pairing correlation survive to longest distance. And the second one is density correlation. Following that, the spin correlation also decay it decay much faster than pairing and the density correlation, but slower than single particle electron hopping. The similar behavior is found for the larger T2 over T1. Now we want to compare this picture with the third quantum phase, which has superconductivity coexist with CDW. Those two figures showing that for different doping levels, like we double the doping, the stripe period is reduced to half, and within each stripe period, we always have 2 electrons. Using the same parameter for this superconducting and CDW coexisting phase, we find that superconducting correlation still decay very slowly and following the power law behavior with a small power law exponent much smaller than 1. Here we also showing the CDW, the pair density correlation. Inconsistent with we have a CDW phase, the pairing correlation also decay power lowly, but with a larger exponent compared to superconducting correlation. So superconducting correlation also very strong in this coexisting phase. This plot shows another point where we have T2 over T1 is much larger than the ones we used before. T2 over T1 is around 0.32. We find that the superconductivity still decays powerfully, but this power exponent is increased to be around 1. So within the third phase, the superconducting correlation may vary, but they remain to be power decay. At the same time, for this superconducting and CDW coexisting phase, we find the spin correlation always decay. The electron gain function always decay exponentially for the 6-leg ladder. But for the 4th-leg ladder, the single particle decay very slowly. So it indicates in the 4-leg ladder, that phase may have gapless like nodes in which makes the electron single particle decay powerfully. In those different phases, the spin correlation always decay exponentially. However, the exponent of spin correlation, it varies for different parameter points, and it increases slightly when we go to the it decreases slightly when we go to 6-leg ladder. So let me go back to have a summary about the 3 quantum phase we obtained. If we fix the filling doping level, then we have CDW, then D wave with uniform density, and then a superconducting CDW coexisting phase. The transition is induced with the increase of T2 over T1. If we fix the parameter T2 over T1, then we can have the transition from CDW to the D wave superconductivity, or from coexisting phase to the D wave superconductivity. In other words, the superconductivity is always becomes more robust as we move towards the optimal doping. So that gives the overall picture of superconductivity and square lattice. I also want to have a brief comparison with the phase diagram of the extended TJ model and triangle lattice. So that is the model we use, including the nearest label hopping, spin exchange interaction, and the second nearest label hopping and exchange interaction. We also included a Kaiser interaction, which involves the spin and the nearest 3 sides form a small triangle. In that quantum phase diagram, even when we go to very small as the 3 spin interaction, we still have 3 different quantum phases with tuning like J2 over J1 or T2 over T1. Those 3 phases are topological superconducting phase with Chern number equals 1, and Chern number equals 2 topological superconducting phase, as well as D wave superconducting phase with Chern number equals 0. We also explicitly show what is the phase at half filling. In this inside topological superconducting phase, at half filling, we can doping antiphase magnetic order phase, which is the phase when J2 over J1 is smaller than 0.007. We can also doping a Kaiser spin liquid, which is the phase when J2 over J1 is larger than 0.07. So the doping antiphase magnetic order state and the Kaiser spin liquid both can lead to topological superconductivity. If we have larger T2 over T1, then doping those Kaiser spin liquid or lemmatic spin wave state, we always obtain the D wave superconductivity. So it indicates topological superconductivity dominates the phase diagram when we move on to the triangle lattice.
Professor Sheng,
yes.
Excuse me. Yes, Alexei has a question.
Yeah, please.
Yeah, I'm curious on the previous slide, the three-spin interaction. Where does it come from? So what is the motivation to include the three-spin term?
Yeah, so there are different possibility for induce this term. One is that if we have a magnetic field, then when you expand the Haber model to TJ model, there's a three-spin interaction. Another possibility is that for some Haber model, if we start from like a twisted TMD system, then the electron hopping itself will carry a phase, which can also result in the Kaiser interaction. But our motivation is try to figure out if we start from the half filling with the Kaiser spin liquid, what kind of superconductivity we can obtain.
Okay.
Then one more question. Even we take out J chi, consider J chi equals zero limit, we also have ongoing work. But in that case, the convergence actually becomes harder because this triangle lattice just like to have some times they also simply breaking terms to settle into the Kaiser topological superconducting phase. Yeah.
Okay. Thanks.
Okay. Yeah, so that phase diagram is obtained based on the combined simulation. One is calculating topological spin pump, which give us the chain number. And the second simulation, which allow us to determine the phase diagram, is the pairing correlation. The pairing correlation shows the power law decay, and for the topological superconducting phase, it can have pairing which is near isotropic. So as illustrated in this figure, we're plotting the pairing and correlation for the pairs along different nearest label bonds. But if we go to the larger J2 over J1 region, which has this D wave phase, then the pairing is much stronger along this direction, B direction. In another two bonds, the pairing is weaker. The ratio between them is around 0.5. So it's a lemmatic superconducting phase. So let me summarize my talk. So we discussed some evidence from experiments that cuprates are related to doped Mott insulators with strong Haber interaction. This is the starting point for our numerical simulation. We showed the global quantum phase diagram for extended TJ model in the T2 over T1 and the whole doping parameter space. We identified that when T2 over T1 is very small, we have stripe phase where the superconductivity is suppressed by the strong CDW order. Then with increased T2/T1, we get into a uniform charge density D-wave superconducting phase. And that phase occupies larger space and expands in parameter space with increasing doping level. The superconducting pairing decays extremely slowly with a power law exponent much smaller than 1. Then we also have superconducting and the CDW coexisting phase. Those are results for the square lattice TGM model. The triangle lattice extended TGM model can have topological D plus ID superconductivity and nematic D-wave superconductivity. Thank you so much.
Thank you, Professor Sheng, for this interesting talk. Let us thank our speaker. And we have time for questions. So perhaps let me start. For the square lattice, the material candidate is cuprates, right? Is there any other materials? And then also, which materials are candidates for the triangular lattice?
Yeah, for the square lattice, I'm not familiar with other material compounds. However, for some ion-based superconductivity, they do have square lattice, but maybe more than 1 bands are required. So for square lattice, I'm not so sure. For the triangle lattice, I think things like transition metal, like a TMD system, that realize Hubbard model. Then if you consider a small twist angle, and so the extended TGM model may be realized in such system.
The twist angle, you mean the bilayer system?
Yeah. Yes. Yeah.
Okay, thank you. Do we have any other questions from the audience?
Please.
Yes, Alexei, please go ahead.
Yeah, I have a very naive question, which I decided to postpone until the end. So how relevant is the antiferromagnetic state that you have before the doping? Can you have similar results if you consider other magnetic states? And yes. Perhaps, I mean, and one very, very naive question, I guess there's something wrong with the ferromagnetic state.
Yeah, we haven't studied the ferromagnetic state because from the large Hubbard model, you obtain the antiferromagnetic exchange coupling. Yeah. Okay. Then for the larger T2/T1, I think numerical T2/T1 or J2/J1, I think the possible magnetic state is stripe phase. So we find the stripe phase can also have upon doping can also have superconductivity to emerge. But yeah, that case may be more consistent with nematic D-wave superconductivity.
Okay, well, basically my question, well, let me refine the question a bit. So
okay.
From the point of view of getting a superconducting state, is it better to have antiferromagnetic state or the stripe order that you mentioned? Does it have any influence?
So the electron doping actually will kill the magnetic order. So that may have some kind of correlation, but it's not fully understood.
Okay. Okay. Yeah, and the other question is related to what, well, partially related to what Dylan was asking. So what I mean, you considered, well, you discussed triangular and square lattice. I also, well, earlier you mentioned Kagoma lattice. So what about the Lieb lattice, which I think is showing up in some cuprates, I believe. So what the TG model gives there?
Yeah, I'm not sure they are recent like DMRG studies. Maybe they are variational studies. So yeah, I'm not sure what's the current understanding. I do know there are some honeycomb lattice simulation, which suggests for honeycomb lattice, they are pairing and they are superconductivity instability upon doping.
Okay, and one more naive question, again related to the Kagoma lattice. So I asked during the talk that perhaps frustration should be beneficial for getting a superconducting order. So now, if you take a Kagoma lattice and just the nearest neighbor TG model, do you get superconductivity there, or it's also not present? Or well, at least, I mean, I remember that I think you mentioned that there are not many results for the Kagoma lattice, so that it's much harder to get them. But even if preliminary, I'm curious.
Yeah, so I have to work in collaboration with Hongzhen Jiang, which we studied several Kagome doping Kagome spin system. We didn't find evidence for superconductivity. At least the pairing correlation usually decay pretty fast for us to label them as a possible superconducting phase.
Okay, so that means, well, most likely there as well you need further neighbor hopping.
Yes, yeah.
Okay, thank you.
Thank you. Yeah.
We have also a question from Sergey.
Yes.
Yeah, this goes back to the starting point of high TC superconductivity discovery and the hype, the never-ending hype in trying to explain the mechanisms. And one of the big questions which I remembered when I was a student, which I heard from the experts in the field, was that there is this problem with the standard BCS theory and the limits set by somewhere around 40K for the transition temperature, and then you got these copper oxide transition temperatures, and then things went on, and I think they went up to, correct me if I'm wrong, something of the order of 200 Kelvin, maybe even, as far as I remember. Now, where are we there at this front? So, because one thing is, if I understand correctly, is to look at let's say models like the Hubbard or the TJ model you discussed here, and to study symmetries of order parameters, to study phase diagrams and the such. But where are we, or where is the research when it comes to numbers, when it comes to reproducing these transition temperatures? Is there some agreement on that corresponding mechanisms from which put into some, so to say, theoretical framework also produce the corresponding transition temperature numbers?
Yeah, so the numerical simulation I'm focusing on, they are pretty limited in terms of predicting the finite temperature results. Analytical simulation, like a slave particle, that can, or variational, that usually give you very high critical temperature from the strong correlated model. So basically, we do not have a good understanding if the strength coordinated system can give the right TC for the cuprates.
Are there any other competing, theory platforms which, as far as I remember, there was a whole inflation at the beginning of all kinds of theory platforms which could lead to new results. Are there any other competing platforms which offer some numbers which are meaningful or not?
So there are definitely still other kind of mechanism, like from phonon or other things. However, I don't think there is a dominant mechanism. So a lot of people believe it's related strength correlation, but it's not settled in terms of what kind of mechanism. Yeah.
It's amazing. It's 35 years since the discovery, if I remember correctly.
Yeah.
Very hard.
Yeah.
Thank you.
Thank you.
Do we have any other questions from the audience? Yes, Sonu Verma, please go ahead.
Hi, am I audible? Sorry.
Yes, we can hear you.
Thank you for the nice talk. I just have a very small question. So when you consider the square lattice and TJ model, then I think you considered Heisenberg kind of nearest neighbor interaction, right?
Yes,
So what about the higher order, higher order interactions?
Like, the high order interaction, like it gives something like a ring change involving force spins. I think if the Kappa model, we think U may be like more than 10 times larger than T, then the ring change term will be very small, which probably won't change the phase diagram. However, if the ring change interaction is much stronger, then it may help with superconductivity. There are some numerical studies with much larger ring change interaction. Yes.
Okay. Thank you.
Okay. Any further questions from the audience? It seems not. So then let us thank Professor Sheng again.
Thank you.
And with this,